Hello, it's Keith here, and this is lesson 5 of the so-called MaxTile series of my 68,000 assembly programming tutorials. MaxTile is, of course, my multi-platform tile map. Uses software, bitmap, where nothing else is available, and it uses the hardware on systems like the Genesis, where there is hardware tile map. Now, what we're going to be looking at today is the so-called cache driver. Now, unlike the previous MinTile tutorials, which I did before, where everything was basically drawn to the screen every frame, MaxTile has a sort of trade-off version where if a double buffer isn't available, we still need to draw directly to the screen, but we want to reduce the amount of flicker, and we can do that in two ways. Firstly, we could draw parts of the screen in sections, and that way, by reducing the amount of draws we do in one go, we reduce the amount of flicker, but also by calculating in advance what needs to be drawn and then doing it all in one go, we don't need to do the calculations in between our drawing phase, and that reduces the flicker again. And that's what you can see happening here on the QL, where memory makes it very hard to use the double buffer because we end up wiping out our system variables. And so we're using these caches here, and so you can see a little bit of flicker here, but it has been reduced by those functions, and it's those functions we're going to be taking a peek at today. Okay, well, let's go over to our code and let's take a look. Okay, so the example here you just saw was SQL MaxTile mid. Mid refers to the middle example, which has the moving sprites on the screen, the simulated sprites. This, of course, uses all of the shared code, and it's actually this file we're going to be looking at today, the so-called cache driver. Now, this is the code for the cache driver, and at the start, the first thing you can see here is the actual template for the cache itself. Now, the cache in all examples here uses 3 entries. The idea is that you could VSync these and synchronize them to the raster beam, so you draw the part of the screen that the beam has finished passing, and that way hopefully the flicker can be reduced to absolutely nothing. I haven't actually implemented that on any of these systems. That's simply because I don't have the time. It was quite hard for me on the CPC, and the CPC, the system I'm most familiar with, so, and you know, trying to do things as precise as synchronizing to beams on all of these systems, I just don't have the time or the requirement to justify it. Anyway, so here are the cache tables, and these are in the same format for every system. It just depends on the system, the settings that are needed. You can see there's some addresses here. These offsets are used to read in the various parameters of each of these caches. And so here's the Genesis cache. And basically, every system, though, they take the same effective format. So the first byte here is effectively the last byte of the VRAM destination that this cache will process. So as we're drawing our lines to the screen and moving down in VRAM, at some point a cache will no longer become relevant to the line we're drawing, and we need to move to the next cache. And so this is the address at which point this first cache becomes no longer relevant, and we need to switch to the second one. And then at some point we need to switch to the third one, and the third one will complete the screen, which is like why the last value is 255. Now, these are 1 byte entries, so they're compared to the top byte of the VRAM destination in all cases, and so we shift whatever the actual VRAM destination is as appropriate. Now, the next byte is, it's not used in any of these examples, but it's designed for the VSync position on the CPC. This was the interrupt count that was the appropriate time to draw this cache, and so they could be used to synchronize. And then finally, we've got 2 copies of the same address here. Well, the address that these will use depends on the system. We actually specify these up here somewhere. Here they are. On the 68,000 systems, we need to allocate 512 bytes. It was 256 on the 8-bit systems, but the 16-bit systems have longer memory addresses, and so we need more memory. So those are the addresses here, and we've got 2 copies because the first copy will be being updated as we're drawing lines into this cache. So that is the current line, the current address of the next free position. The second one is the sort of constant one that is used to write back to the first one when the cache is cleared. So that's why we have that format there. So those are the cache definitions here, and we have a routine called get cache IY. Now the IY in question referred to the IY register on the Z80. On the 68,000 systems, we use register A5 as the equivalent here. Now what this is going to do is it's going to read in the address of the cache from the pointer in A5. So we're moving to the address back, which is the base address of the cache that it never changes. And so this is when we're planning to draw this cache to the screen. We want to start at the beginning of the cache and move all the way through to the end of the cache. So that's why we're using the backup address that never changes there. Now what we're doing next might look a little bit odd. what we're doing is basically we're ORing the next 6-bit bytes in the cache together and then returning. The reason we're doing this is that on the 68,000 base systems, a 6-0 entry in the cache will actually represent the end of the cache. On the Z80 and the 6502 it was 4 bytes, but again we need 2 extra bytes for our memory addresses here, so it becomes 6. So that is the cache empty sequence there basically, and so we're setting the 0 flag accordingly to that. Now here we've got the draw tile map routine. Now if you saw last time's example with the direct driver, which is the precursor to this, I wrote the direct driver first and this was the enhanced version, but this is the equivalent here. It doesn't actually draw to the screen, it draws into the caches, and then we need to flush the caches to the screen. Now what this is going to do though is it's going to start the drawing procedure and then fill the caches as required with the data. So the first thing we're doing here is we're loading the address of the cache table here. And what we're doing here is we're taking the first byte that represents the last VRAM address that this cache will process. We're taking the address of this cache as well and we're loading it into A4 here. And this is getting us ready to start up. So what we're doing now is we're going to basically take the current VRAM destination and we're moving it in D0. And then we've got some bit shifting commands that are platform specific, because some of these systems use 16-bit addresses, some use 24-bit addresses. It really varies how many bit shifts we need to do and things to get the top byte of the VRAM destination that we want to compare to that byte that we read in from the cache definition up here. So we're shifting them and then we're comparing here and we're seeing if the top byte of the VRAM destination exceeds this current cache entry. Now if it does, we need to move to the next cache, and the way we do that, we're writing the end marker for the cache here to show that to make sure that this cache has been marked as no longer in use. And then what we're doing here is we're basically moving to the next cache entry here by moving the number of bytes that each cache contains here, and then we're returning, and that would start us up again at the position we just saw up here. So at the point that we get to sort of this position here, we're actually going to start drawing data into the current appropriate cache. Now D7 is being shared with 2 values here, each of which is a byte. Basically we need to remember the first tile position and the last tile position so that we can work out the count for the tiles that we need to draw. Now this is using the width of the line in tiles as the count, and so the first entry will actually be higher than the last entry. The first entry may be 36 and the last entry might be 4, something like that. And so both of those are stored in 2 bytes within that single register, and that's because I was running out of registers compared to the Z80, so we're showing one register with 2 values there. Okay, so we're going to do a single line of our tile map here. We're loading a single byte in from the tile map data. Now the data is designed to be in little endian format, so even though the entries are 16 bits, we work at 8-bit parts here. So we're taking the first byte here. Now the least significant bit of that is the update flag, and so we're checking that update flag here, and if it's clear we're skipping over to tile empty. If it's set, then we need to draw this tile to the screen. So the next thing we're doing here is we're checking to see if that value in D7 has got the first tile marked, because if it has, then we don't need to do this next stage. But if it's not got the first tile marked, then we've just found the first tile on a line that needs to be drawn. So what we're going to do here is we're going to take our current tile position on this line, effectively the loop counter here, and then we're going to basically move that into the second byte here. We're adding 1 to it though, and that's because we need a count of 1 for a single tile, and in that case the first and the last tile entry would be the same if we didn't add 1 there. So that's why we're adding 1 there. Okay, and then once we've done that, basically we're going to continue. But there's another thing we need to do. Now maybe this isn't just the first tile on the line, maybe it's the first tile in the tile map. Now that has a special requirement. Multiple tile maps can work with different pattern data with MaxTile, and so we have an address for the pattern data, and because of that, if we're drawing a new tile map, we might need to set a new tile map tile pattern address for the drawing routine. And if that's the case, we're going to write that in here. Now, this has a special sequence of bytes. The first byte has to be 0. The second byte is also 0. That's in some cases not used. And then the next 4 bytes are the address of the pattern data that we're using. And that's why the empty cache sequence is 2 0 bytes followed by 4 0 bytes, because the pattern data update is 2 0 bytes followed by 4 non-zero bytes. And that's what we're doing here. So we're writing our address of our pattern data here. We do have in some systems an extra byte here that's written into that second byte at offset 1, and that's a tint. Now what this is I'm tending to favor 4-color data these days, 4-color pattern data on all systems, even 16-color ones. And the tint is effectively toggling between the possible 16 colors when I'm using the 4-color source data and drawing to the 16-color screen. And so that's what that tint would be on those systems. Anyway, whether there's a tint or not, we're adding 6 to our cache entry, and then we're ready to start drawing the data here. So it's not the first tile of the cache, but it is the first tile of the line. So what we're doing here is we're writing our VRAM destination into the cache, and then we're writing our tile map source into the cache as well for this line. And again, these would have been 2 bytes on the 8-bit systems. They're 4 bytes on the 16-bit ones, and that's why the caches have to be 12 bytes on the 16-bit systems. So that's basically putting the marker for the first line, and then the only other thing we need now is a count of how many tiles we need to consider for drawing when we actually get to the job of pumping data to VRAM, and that happens later, of course. So there we go. So that's what's happening there. So we've now finished processing this new entry, if there was one. So this is now just the line that we do for a non-empty tile. What we're doing here is we're writing the tile count into the low byte of D7 here. D7, the second byte is the first tile number, and this is effectively the current tile number, which at some point, of course, will be the last tile number if we don't find any valid tiles, and so we're just updating that for later. Whether we found a tile to draw or not, though, we move to the next entry within our source tile map here by adding 2 bytes per tile entry. And then we need to update our VRAM destination to move across the screen to the next position. And then we need to basically repeat until we've done all the tiles on the line. Now, once we've processed an entire line of our source tile map, it's time to actually look at what we found. Did we find any tiles to draw? And if so, how many? And that's what we're doing here. We're taking basically the second byte in D7, which is the first tile number, and we're moving that effectively into D0 here. We're shifting it into the appropriate position. And then we're subtracting the last entry. Now, remember I said that the first entry will actually be the higher number because we were using the loop count. So this might be 10, this might be 5, and that would mean there's 5 entries within our line. Remember we added 1 to this value here, so that we get a valid count if both were a single tile. Maybe there was just 1 tile on a line, and if we had 5 as the first and 5 as the last and we subtracted them, we'd end up with 0, and there's not 0 tiles to draw, there's 1 tile to draw. So that's why we did that there. Now if we find that there's no tiles to draw, we simply skip over here, but if there are tiles to draw, we write our tile count into the current line. Now we've already written in our VRAM destination and our patterns tile source here. So the last thing that we need is the count of the tiles on this line, and that's what we're doing there. So rounded up to 16-bit word aligned, we've written 10 bytes here. That's 1 byte for the tile count. That's 4 bytes for the VRAM destination and 4 bytes for the tile map source. So we're updating our position in the cache here. What we're doing now is we're checking if we've actually filled the entire cache here. We would limit the tile cache to around 500 bytes. It can take 512, but we can't fill it up, otherwise we'd lose data. If it's full, then we flush it straight to the screen. This is very, very rare. It's theoretically possible though, so there's a facility, and that would just say, my cache is full, I need it empty, just dump it to the screen now and clear it out again. So that's what happens there. Now once we've done a line of our screen, we need to move it down to a line in VRAM, and that's what these lines are doing here, platform specific to calculate the next line. And then once we've done all the lines of our tile map, considered them and added any lines to the cache, we're done. And so in that case, we simply write the end of the cache and we return. Now, of course, the one important thing to bear in mind is if we had a tile map where the first line had changed and the last line had changed, the cache would only contain 2 lines, because a completely unchanged line with no update flags is never written to the cache at all. And that's how we save the processing power when it comes to drawing these to the screen. So here's the cache full routine here. So this is just basically backing up all our registers, getting the address of the current cache, and then it's running the process cache routine, which dumps it to the screen. That actually draws it. And so that's just saying I give up. I'm full. I need to be empty, and it's flushing it to the screen, and then it's loading the new address of the cache as being the start of the cache. So the cache was full. We flush it down, and then we start from the empty position again. That will cause flicker, but there's no choice. The cache is full. We need more data. We need to write more data into it. I think that might happen if if literally every single thing on the screen has changed. It might happen. I'm not even sure about that. It might even need multiple sprites on the screen before that would be a risk. You could change the cache size from 512 bytes to 1024 or more if you want anyway. The 512 is not the upper limit. It's just a good balanced amount that doesn't use too much memory, but gives a good acceptable level. Okay, so here's the reset caches routine. Now this would be executed after all the caches have been flushed to the screen. So all we're going to do is take the number of entries in our cache, move to the first cache table, and it copies the backup address to the current address for all of the caches. So that just basically resets all the caches, setting the address to use next at the very start, and then we're returning there. That's all there is. Okay, so here's our process cache routine, and this actually draws a cache to the screen. So in the case we're using double buffering, we wouldn't actually do this, but that would be you really usually wouldn't have that configuration. Usually you'd be using the dark driver. I've got a few bits of code in here from testing versions where I was doing very logical things to actually see what was going on. So that's the only reason that's there. That wouldn't ever actually happen. So what we're doing here is we are moving the first byte from our cache, and we're basically comparing that to 0, because if that's 0, this is a command byte. That means it's either the end of cache marker or it's the pattern addresses, and so we would jump down in that case to process cache 0. Otherwise, this must be a line of actual data. Now that would be the count of the tiles on this line if it's not a 0. And so what we're taking next is the VRAM destination and the tile map source here. Now what we're going to do is basically process all of the tiles on this line. We've got some test code here to slow down the drawing in case you need to see what's going on. But what we're doing here is we're basically taking the first byte from the tile map here, and we're shifting 1 bit out. Now if the carry is set, this needs to be drawn to the screen. If the carry is clear, it does not. Now actually we would know that the first tile needs to be drawn to the screen, otherwise it wouldn't be in the cache. But the tiles in between, we know the first and the last must be need drawing, but tiles in between may be transparent, and we would need to skip over those, and so that's why we're still checking that update flag here. Once we've drawn a tile to the screen, we need to move the VRAM across again, because again we know the starting VRAM address, but we need to calculate the VRAM address of the next tiles as we're drawing a line here. Now once we've done a line, we simply move to the next line entry within the cache, and we repeat. There's no code to move down a line in VRAM because each line has a separate entry in the cache, and the VRAM destinations have all been calculated. I've decided to do things this way. I mean, you could argue that maybe it would have been better to calculate the VRAM destination here in real time, or maybe do some alternate way rather than do all of these update of the VRAM destinations. This is the way I decided to do it. I'm not saying it's the only way, it certainly isn't. I'm not saying it's the perfect way. It's just it seemed the correct balance in my mind. Anyway, so that's how we process the caches. And then the final thing here we've got is process cache 0. Now this is when we've detected that command byte where the byte that should be the count of tiles is actually 0. So this is effectively either the end of line command, or this is an updated pattern address if we're drawing a new tile map to the screen. So we're just going to test that here. If we've got a tint, we're loading that in there. If we have or if we haven't, though, what we're doing here is we're loading the address that would be the pattern address. However, if that is 0, if all 4 bytes of that is 0, then this is actually the end of cache marker. In that case, we're writing the end of the cache and we're returning here. If it's not, though, then this was actually a legitimate pattern address, so you would get that the start of a new tile map. And so in that case, we need to actually basically return to our original position, skipping the 6 bytes. That's the 2 bytes that would be the 0 byte for the command marker, the byte for the tile tint if applicable, and the 4 bytes for the pattern address. And so in that case, we're returning back up here, and we're doing the same again. I mean, you could argue we don't need to check for the pattern 0 there, but D7 is also the loop count here, so we do need to load that in with a valid loop count. Anyway, there we go. So that's this example. We're going to continue with MaxTile on all of the systems. Next, we're going to be looking at the platform-specific modules. That's the drivers that draw a single tile to the screen on every system. I've said before, MaxTile is very complicated. It had to be because of what I wanted it to do. And so if it's too much for you, or if it's too little for you, and you're far better than I am, I'm sure it's very possible, you're probably able to write something better of your own. But maybe you want to see the individual drawing routines for each system, with the X flip and Y flip. Maybe you could get some ideas, or maybe you could use that even if you don't want to use the rest of MaxTile, because it's a totally standalone module. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.